Hello guys, welcome to my class on the topic of integration, and this is class number 9. In this class I will cover a subtopic of integration of trigonometric identity by using T formula substitution. I'm Engineer Goodluck, and you can contact me through my email goodluck.laudk@gmail.com, and I'm Tanzanian. Okay, we use T formula for the integral of the form 1 integral of d theta over sine square of theta. When you have this kind of integral where the denominator has a trig identity whose power is raised to 2 plus or minus a constant, we use T formula. Or integral of the form of d theta over a constant which is 1 plus or minus cos theta times sin theta. In this type of integral we use T formula. Or integral of the form of sin square of theta, or can be cos square of theta d theta over a constant 9 plus or minus sin square of theta. Or integral of the form of d theta over sine of theta. This is a special case for T formula. I will show you in examples. Or integral of the form of d theta of cos theta as well. This is a special case. This d theta cos theta, d theta cos theta, and d theta sin theta. These are special cases of T formula because they have no power of 2. Here there is power of 1 and the power of 1 as well. There is not a multiple of 2 trig identity. It means either sin theta cos theta or sin theta tan theta. As well, in this case, there is no power 2, even there is no multiple of 2 trig identity. I mean, either sin theta cos theta or sin theta tan theta or cos theta tan theta. Okay. We will show in examples how to solve this kind of integral for case 5 and case 4. For case 3, 2, and 1, these are simple because they hold T formula properties. Okay. In T formula, we let T is equal to tan of an angle of trig identity under the under the integral. So we assume T is equal to tan of theta. Let's assume this T is equal to tan of theta. It means the expression under the integral has an angle of theta. In this case, when you draw a right-angled triangle, this angle theta is this one, so tan theta is opposite T. Opposite is T over adjacent, which is 1. So in this area we have 1. So hypotenuse is T square plus 1 square. Hypotenuse is T square plus 1 square. So from this triangle, sine of theta will be equal to T over square root of T square plus 1. And cos of theta will be 1 over under root of T square plus 1. So we have the T formula for tan theta, sin theta, and cos theta. Okay. T formula is valid for expression whose denominator, as I told you earlier, has cosine or sine raised to power of 2, or cos whose denominator has cos of theta times sine of theta, or has the cos of theta times tan of theta, or has the sine of theta times tan of theta. I mean, whose denominator has a multiple of two identity of trig, either cos theta or sin theta. We see other identity, maybe tan theta times tan theta, cos theta times sin theta, sin theta times tan theta, and so on. Okay, consider the following examples. Example: integrate d theta over 1 minus sin square of theta to integrate d theta over sine of theta. I pick this is two examples because one hold the T formula properties and the second one does not hold the T formula properties, because in example number 1 denominator has power of 2, but in example number 2 denominator has power of 1. So let's look on example number 1. Integral of d theta over 1 minus sin square of theta. In this case, my theta, I let t is equal to tan of this angle, which is theta. So when I differentiate dt with respect to theta, I get this value. Dt is equal to sec square of theta d theta. But what is sec square of theta? It is 1 plus tan square of theta, which tan theta is equal to t, so is 1 plus t square. So where sec square of theta is equal to 1 plus t, this t square d theta. So I will replace, where there is d theta, I will replace dt over 1 plus t square. Okay. Where d theta, I will replace dt divided by 1 plus t square. Okay. We have integral of d theta over 1 minus sin square of theta. In this case, where d theta, I place dt over 1 plus t square, and where there is sine square, where there is sine of theta, I place t over under root of 1 plus t square. So when I place this two, d theta is equal to this one and sin theta is equal to this one, I have the following function is equal to integral of d theta, which is dt over bracket 1 plus t square bracket 1 minus sin square theta, which is sin theta is equal to this one. There will be t square minus t square over 1 plus t square. So what I get is a dt over 1 plus t square, 1 plus t square bracket times 1 plus t square becomes in this position minus t square. So t square and t square goes, I remain with 1 over 1 plus t square. So I remain 1 over 1 plus t square. Okay. So this one and this one cancel, I remain with dt. I have integral of dt. When I integrate this one, I get t plus constant, but what is the value of t is tan of theta plus constant, and this is my result. Okay, let's look on example number 2, the theta over sine of theta. In order to integrate this type of function, we must use T formula, but T formula holds for function whose denominator has sin theta or cos theta Oh, okay. Let's look for example number 2. We have sine d theta over sine of theta. In order to integrate this type of function, we must use T formula. But T formula holds for function whose denominator has sine of theta or cos of theta or tan of theta raised to power of 2, or it has denominator of the form sine of theta times cos of theta or sine of theta times the tan of theta or cos of theta times tan of theta. But and so on. But what about this denominator, which is sine of theta, has power of 1? In this case, we transform sine of theta into double angle identity. So we have the following. Sine of theta is equal to 2 sine of theta over 2 times cos of theta over 2. So in this case, we change sine of theta to sine dot cos. So instead of using sine of theta, I will use 2 sine theta over 2 cos theta over 2. And so where there is sine of theta, I place this identity. Okay, so which is equivalent to sine theta over 2 cos theta over 2. Okay, so I let t is equal to tan of an angle which is theta over 2. So t is equal to tan of an angle under consideration which is theta over 2. When I differentiate dt, I get what? Sec square, half sec square of theta over 2. A half sec square of theta over 2 d theta. Okay, so from this integral of d theta over sine of theta, I replace sine of theta with 2 sine theta over 2 times the cos theta over 2. Cos theta over 2. Where we saw dt over a half bracket sec square of theta over 2, which sec square of theta over 2 is equal to 1 plus tan square of theta of 2, and tan of theta over 2 is t. So we have a half bracket 1 plus t square. This is equal to d theta, and as well sine of theta over 2 is equal to t over square root of 1 plus t square. As well, cos of theta over 2 will be equal to 1 over under root under root of 1 plus t square. So when I substitute this expression into this integral, I have, where there is d theta, I put this one. So I have dt over a half 1 plus t square in the place of d theta. Okay, in the place of d theta, I put this one, which is the dt over bracket over a half brackets 1 plus t square, and times bracket 2, whereas I sin theta over 2, I put this one, which is t over under root of 1 plus t square, and whereas I is cos theta over 2, I put this one, which is 1 over under root of 1 plus t square. So t times 1 is t over under root of 1 plus t square times under root of 1 plus t square, I get 1 over 1 plus t square. Here I get 1 plus t square bracket. So when this and this cancel out, and a half and a 2 cancel out, we remain with the integral of dt over t, which is equal to ln dt over t integral is equal to ln of t. So we have ln of t plus constant. Okay, what is the value of t? We see value of t is equal to tan theta over 2. So we have ln of tan of theta over 2 plus constant. So tan of theta over 2 plus constant. Okay, see you in next class number 9.